Imagine a visitor from beyond our solar system, carrying secrets billions of years old, just caught by the James Webb Space Telescope. This isn't just any space rock, it's a time capsule that's rewriting our understanding of the universe. Don't miss a cosmic beat. Subscribe now. Our story begins with the silent, constant watch of the heavens. Every night, robotic eyes scan the darkness, looking for anything that moves, anything that changes. They're our planet's first line of defense, and our first window to the unknown. The sky's a vast and lonely place, filled with stars that have been in their positions for longer than human history. Against this fixed background, our own solar system family, the planets and asteroids, move in slow, predictable dances. We know their steps, we have mapped their paths, but in the summer of 2025, this familiar dance was interrupted. We can now look back and see how it all started. It began with an alert, a small flag in a sea of data. This is the story of the Cosmic Intruder alert, and our first meeting with a traveller named 3I Atlas. In July 2025, a special survey system was doing its job. This system is called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System. Its main purpose is to find asteroids that might come too close to Earth. It's like a cosmic security guard watching for danger. ATLAS is made of several telescopes that work together, taking pictures of the sky over and over again. Computers then compare these pictures, looking for tiny dots of light that have moved. Most of the time, these dots are known asteroids, following their usual routes around the Sun. But on one particular night, the computers found something different. They spotted a faint object moving in a strange way. It was moving against the backdrop of distant stars, but its path was not like that of a normal asteroid or comet from our solar system. Its trajectory was unusual, its speed was high, and its direction suggested it was not one of ours. This was not a familiar neighbour dropping by. This was something new. The computers flagged it for human eyes to check. Astronomers looked at the data, their curiosity growing. They tracked its movement over the next few nights, confirming the strange path. The more they looked, the more they realised this was not a member of our solar system family. It was a visitor from far, far away. The object was given a name, 3I Atlas. The name itself tells a story. The 3I part is very important. I stands for Interstellar. This means the object came from the space between the stars. The 3 means it was only the third interstellar object ever confirmed to have entered our solar system. The first was a strange cigar-shaped object called Oumuamua, which sped through in 2017. The second was a more comet-like object named 2I Borisov, discovered in 2019. Now, we had a third, and Atlas was added to the name because the Atlas survey system was the one that found it. So, 3I. Atlas literally means the third interstellar object discovered by Atlas. The name itself was a declaration that something special had arrived. Scientists around the world felt a rush of excitement. Finding one interstellar object was amazing. Finding a second was incredible. But finding a third confirmed that these visitors might be more common than we ever thought. Each one is a priceless opportunity, a chance to study a piece of another star system up close, without having to travel for thousands of years to get there. It's like a message in a bottle, not from across an ocean, but from across the galaxy, washing up on our shore. And this new message, 3I Atlas, was headed our way. To understand why 3I Atlas caused such a stir, we have to understand what interstellar really means. It means this object came from a star system that is not our own. Imagine our solar system is a single house on a very long street. All the planets, asteroids and comets that belong to our Sun live in or around this house. An interstellar object is like someone from a house many miles down the road, walking past our front door. It was born around another star, a different sun, in a different part of the galaxy. It travelled for an incredibly long time, perhaps millions or even billions of years, through the cold, dark emptiness between the stars. It journeyed through the void, alone. This long and lonely trip is what makes it so special. It carries with it the chemical clues of its birthplace. The materials it is made of are a direct sample of the stuff that was present when planets formed around its parent star. By studying 3I Atlas, we are not just looking at a rock. We are looking at the building blocks of another world, a world we may never see. It's a piece of galactic history, delivered right to our neighbourhood. The information it holds could tell us if other solar systems form in the same way ours did, or if the galaxy is filled with a huge variety of planetary systems, each with its own unique story. The first two interstellar visitors left scientists with more questions than answers. Oumuamua was the first. It was detected as it was already leaving our solar system, so we only got a brief look. It was small, dark, and shaped perhaps like a cigar or a pancake. It didn't have the fuzzy cloud or coma that comets usually have. This made it very mysterious. Was it a new kind of comet, an alien piece of technology, or just a strange space rock? We still don't know for sure. It left us puzzled and wanting more. Then came 2I Borisov. This second visitor looked much more like a regular comet. It had a visible coma and tail made of gas and dust. Scientists were able to study it in more detail. They found it had chemicals similar to the comets in our own solar system, but with some key differences, like a very high amount of carbon monoxide. Borisov showed us that comet-like objects do exist around other stars and can be thrown out into the galaxy, but it was just one example. Now, with 3I Atlas, we had a third chance, a third data point, a third messenger from the great beyond. Scientists hoped this new visitor would help solve the mysteries left by the first two. Would it be strange and unexplainable like Oumuamua, or would it be more familiar like Borisov? The arrival of 3I Atlas was a chance to build a better picture of these cosmic wanderers and their origins. It was an opportunity to finally start understanding what kind of objects are floating in the vast ocean between the stars. One of the most striking things about 3I Atlas was its speed. It was moving incredibly fast. Scientists calculated its speed to be about 210,000 kilometers per hour. That's almost 60 kilometers every single second. This speed is far too fast for it to be captured by our sun's gravity. It's like a car driving so fast it can't make a turn and just keeps going straight. 3I Atlas was not here to stay. It was on a path that would take it on a single sweeping flyby of our sun. This path is called a hyperbolic trajectory. Imagine throwing a ball. If you throw it slowly, it will arc and fall back to the ground. If you throw it fast enough, it will go into orbit. But if you could throw it with incredible speed, it would fly off into space, never to return. 3I Atlas is on that kind of path. It came from deep space, it will swing around our sun, and then it will shoot back out into deep space, continuing its endless journey through the galaxy. This one-time visit makes every single moment of observation precious. There are no second chances. Whatever we can learn from it, we have to learn now, before it disappears back into the darkness forever. This fleeting encounter adds a sense of urgency and drama to the mission of studying it. This brings us to a key difference between 3I Atlas and the comets we are used to. Comets from our own solar system, like Halley's Comet, are members of our sun's family. They live in the cold, outer regions of our solar system, in places called the Kuiper Belt and the Oort cloud. They travel on long, oval-shaped orbits that bring them back towards the sun again and again. Halley's Comet, for example, returns every 76 years. We can study it, wait for it to come back, and study it again. We know it will return. But 3I Atlas is different. It is not in an orbit around our sun. It is a true wanderer. It is a one-time visitor, a messenger that will never return. Once it passes through our solar system, it will be gone for good. It will continue its journey among the stars and we will never see it again. This makes 3I Atlas incredibly valuable. It's a rare, limited-time opportunity. It's like an ancient ship from a lost civilization sailing past our shores just once. We have to learn everything we can from it before it sails over the horizon and vanishes forever. The data we gather today will be all we ever have of this mysterious object. This single fact shaped the entire scientific response to its discovery. It was an all-hands-on-deck moment for astronomy. The world's greatest telescopes had to be pointed at this fleeting target to capture its secrets before it was too late. The pressure was on to make this encounter count. Still with us, because the story of 3I Atlas just gets wilder, revealing secrets that could rewrite history. The discovery of 3I Atlas sent a wave of urgency through the scientific community. Here was a visitor from another star system, a target moving faster than almost anything we had ever tried to track. To study it, humanity would need its best instrument, its most powerful eye in the sky. That eye is the James Webb Space Telescope. But catching a glimpse of this faint speeding object would be a monumental challenge. a true test of technology and human ingenuity. It was like trying to photograph a single, fast-moving firefly in a huge, dark forest from miles away. This was the moment for Webb's unbelievable catch, a true needle in the cosmic haystack. On August 6, 2025, the impossible happened. The James Webb Space Telescope, also known as JWST, successfully locked onto 3I Atlas. It captured not just pictures, but detailed data from the fast-moving comet. This was a huge victory for the mission. It proved that Webb was capable of tracking even the fastest and faintest objects in our solar system and beyond. When Webb was designed, its main job was to look at things that were very far away and seemed to be standing still, like distant galaxies. Tracking a nearby object moving at high speed was not its primary design goal. It was a capability that scientists and engineers had to carefully develop and test. Successfully observing 3I Atlas showed that all that hard work paid off. Webb's tracking ability was even better than they had hoped. This achievement opened up a whole new world of possibilities. It meant that if another interstellar object visits us, Webb will be ready. It can study fast-moving comets, asteroids, and other objects with a level of detail that was previously unimaginable. This single observation wasn't just about one comet. It was about proving a powerful new tool for exploring our cosmic neighborhood. The challenge of this observation cannot be overstated. From Webb's unique position in space, the task was incredibly difficult. The telescope doesn't orbit the Earth. It orbits the Sun at a special spot about 1.5 million kilometers away from us, a place called Lagrange Point 2, or L2. From this distant viewpoint, 3I Atlas appeared as a tiny, barely visible speck of light. And this speck was racing against a background of faraway stars. To Webb, the comet's apparent speed across the sky was very fast. The telescope had to pivot smoothly and perfectly to keep the comet centered in its view. If its movement was off by even the tiniest fraction, the comet would drift out of the camera's frame, and the observation would fail. It's like trying to keep a camera focused on a speeding bullet, while you are also moving. The level of precision required was astonishing. The background stars would appear as streaks of light in the images, because the telescope was moving to follow the comet, not the stars. This tracking was a delicate dance between the telescope's hardware and the complex software that controls it. To make this observation happen, scientists had to perform some of the most precise calculations of their careers. They had to know exactly where 3I Atlas would be at the exact moment Webb was scheduled to look at it. This is harder than it sounds. The comet's path could be slightly changed by things like gas shooting out of its surface, so they had to model its trajectory with extreme accuracy. They also had to calculate its path relative to Webb's own orbit around the Sun. Both the telescope and the comet were moving through space. It was a complex problem of orbital mechanics. The scientist had to predict the comet's position so perfectly that it would appear right in the very narrow field of view of Webb's instruments. A tiny error in their calculations, a misjudgment of its speed or direction, would mean the telescope would be pointing at empty space. All that precious observation time would be wasted. For weeks leading up to the observation, teams of experts double-checked and triple-checked every number, running simulations to make sure their plan was perfect. The success of the observation was a testament to their skill and careful planning. Webb did more than just take a picture. It used one of its most powerful tools, the near-infrared spectrograph, or NIRSpec. This instrument is special because it doesn't just see light, it breaks light down into its different colours or wavelengths, like a prism. This creates a spectrum, which looks like a rainbow with dark and bright lines. These lines are like chemical fingerprints. Each gas, like water or carbon dioxide, absorbs and gives off light at very specific colours. By looking at the spectrum of the light from 3I Atlas, scientists could see exactly what gases were present in the fuzzy cloud around it. This fuzzy cloud is called the coma. NIRSpec allowed them to not just identify the gases, but also to map where they were. They could see how the gases were distributed around the comet's solid core or nucleus. They could measure how much of each gas there was. This is an incredibly powerful technique. It's like being able to analyze the air in another part of the world without ever leaving your home. Webb was able to perform a remote chemical analysis of a visitor from another star system, giving us our first real look at its composition. This amazing achievement showed just how much more powerful Webb is compared to older telescopes. A telescope like the Hubble Space Telescope is incredible, but it primarily sees visible and ultraviolet light. Webb is designed to see infrared light. This is important because many molecules, including the ones that make up a comet's coma, give off strong signals in the infrared. Webb can see these chemical fingerprints much more clearly than Hubble can. Ground-based telescopes on Earth also face a major challenge: our own atmosphere. The Earth's atmosphere absorbs a lot of infrared light, making it difficult or impossible to see the faint chemical signals from a distant comet. Webb, being in space, has no atmosphere to look through. It has a crystal-clear view of the universe. This combination of seeing in infrared and being above the atmosphere gives Webb a huge advantage. It can see things that other telescopes simply cannot. The observation of 3I Atlas was a perfect example of this. It captured details that would have been completely missed by any other observatory. This success proved that Webb is not just a tool for looking at the distant past, it is also our most powerful probe for exploring the mysteries that wander into our own cosmic backyard. It has truly changed the game for planetary science. The data gathered by NIRSpec was sent back to Earth as a stream of ones and zeros. Scientists eagerly began to process it, turning the raw data into meaningful information. The first images and spectra started to appear on their screens. What they saw was stunning. The tracking had been perfect. The data was clean and clear. The chemical fingerprints were strong. For the first time, humanity was getting a direct look at the raw ingredients of an object born in another solar system. The excitement in the scientific community was electric. This was the moment they had been waiting for. They were about to unpack the secrets of 3I Atlas, a messenger that had travelled for billions of years to reach us. The information hidden in that light, captured by Webb's golden mirror, was about to start a revolution in our understanding of how planetary systems are made. The needle had been found in the cosmic haystack. Now it was time to see what message it carried. The first results would be more shocking and more exciting than anyone had dared to imagine. The story of 3I Atlas was about to take a very strange turn. As scientists began to analyse the data from the James Webb Space Telescope, they were looking for the familiar signatures of a comet. They expected to find water, the molecule that is the lifeblood of comets in our own solar system. But as the chemical fingerprints from 3I Atlas came into focus, a gasp of surprise spread through the research teams. The data was clear, but it made no sense based on what they knew. It was like opening a letter from a faraway land and finding it written in an alphabet you've never seen before. The comet was speaking a chemical language that was alien to us. This was the beginning of a major discovery, a chemical time capsule holding a carbon dioxide surprise. Webb's analysis of the light from 3I Atlas revealed something extraordinary. The comet had an extreme chemical makeup. It was unlike anything scientists had ever seen before, either in comets from our own solar system or in the previous interstellar visitor, 2I Borisov. The balance of ingredients was completely different. In our solar system, comets are often called dirty snowballs. This is because they are mostly made of water ice, mixed with dust and rocks. As they get closer to the sun, the heat turns the water ice directly into gas, a process called sublimation. This water vapour forms the vast, fuzzy cloud around the comet's core, known as the coma. But 3I Atlas was not a dirty snowball. It was something else entirely. Its chemical signature was dominated by a molecule that is usually only a minor ingredient in our comets. This single fact would force a complete rethinking of what an interstellar comet could be. The time capsule was open, and its contents were challenging decades of scientific understanding. The biggest surprise, the one that made everyone stop and stare at their data, was the overwhelming amount of carbon dioxide. The fuzzy cloud, or coma, surrounding 3I Atlas was not mostly made of water vapour. Instead, it was almost entirely composed of carbon dioxide gas. This was a stunning revelation. Carbon dioxide, the same gas we breathe out, was the main driver of this comet's activity. Usually carbon dioxide is present in comets, but in much smaller amounts compared to water. Here, the roles were completely reversed. It was as if someone had built a car where the windshield wipers were the size of the engine, and the engine was the size of a small button. The proportions were all wrong, based on everything we knew. This discovery immediately set 3I Atlas apart from every other comet we had ever studied in detail. It was not just a little different, it was fundamentally different in its basic chemistry. To put this discovery into numbers, Webb's instruments found that 3I Atlas had about 8 times more carbon dioxide than water vapour. This is one of the highest ratios of carbon dioxide to water ever found in any comet. For most comets in our solar system, the ratio is the other way around, with much more water than carbon dioxide. This massive amount of carbon dioxide is a game changer. It's making scientists completely rethink their models of how comets from other star systems might form and how they change over time. It suggests that the birthplace of 3I Atlas was very, very different from the birthplace of our own comets. The abundance of a particular chemical is a direct clue about the conditions under which it formed. A comet rich in water ice likely formed in a place where temperatures were right for water to freeze. A comet rich in carbon dioxide ice, like 3I Atlas, must have formed in a place where carbon dioxide was the main substance available to freeze onto its surface. This was a powerful clue, pointing to a very different kind of planetary nursery. To understand why this is so surprising, let's think about regular comets from our own solar system. They spend most of their lives in the frigid, outer darkness, far from the sun. In these cold regions, water exists as hard ice. As a comet's orbit brings it into the inner solar system, it starts to warm up. The sun's energy hits its surface. The first ice to turn into gas is usually the most volatile, like frozen carbon monoxide or nitrogen. But as the comet gets closer and hotter, the water ice begins to sublimate. Since there is so much water ice, this process releases huge amounts of gas and dust. This is what creates the familiar bright coma and the long flowing tails that we associate with comets. Water is the main engine of their activity. We see this time and time again with comets like Hale-Bopp or Halley's Comet. Their spectacular displays are powered by the transformation of water ice into gas. 3I Atlas, however, was telling a different story. Its engine was not water. Its engine was carbon dioxide. This meant it could become active much farther away from the sun, where it is still too cold for water ice to turn into gas. Its behaviour was dictated by a completely different chemical process. This makes it a truly alien object, operating by a set of rules we are only just beginning to understand. The discovery of the carbon dioxide dominance in 3I Atlas was a moment of pure scientific excitement. It was the kind of discovery that changes textbooks. It showed that our ideas about comets, based only on the ones in our solar system, were too narrow. We had been looking at just one type of comet, born in one specific environment. We were like people who had only ever seen oak trees and assumed that all trees everywhere must be oak trees. 3I Atlas was a sequoia, a palm tree, a mangrove, something completely different that showed us the diversity of nature. The universe, it seems, has more than one way to build a comet. This realization opens up a universe of new questions. How many other types of comets are out there? What other strange chemical makeups will we find in future interstellar visitors? 3. Atlas wasn't just a discovery. It was an invitation to explore a much wider, more diverse cosmos than we had ever imagined. The chemical time capsule had delivered its first and most profound secret. The story of planetary formation across the galaxy had just become a lot more interesting. This revelation immediately prompted a re-evaluation of the other interstellar objects. Could Oumuamua's lack of a visible coma be explained if it was made of something that didn't produce visible dust when it turned to gas? Did 2I Borisov's high carbon monoxide content hint at this larger trend of non-water dominated objects? 3I Atlas provided a crucial new piece to the puzzle. Its extreme chemistry was a clear signpost, pointing toward a new understanding. It suggested that interstellar objects might not just be visitors, but teachers, here to show us the full range of possibilities that the galaxy holds. The carbon dioxide surprise was more than just a chemical curiosity. It was a fundamental shift in our perspective. It was the universe telling us, once again, that it is far stranger and more wonderful than we can imagine. The discovery that 3I Atlas was overwhelmingly rich in carbon dioxide was like finding a key. This key didn't open a treasure chest, but something far more valuable. A window into the past, looking at a place we can never visit. The chemical makeup of a comet is its birth certificate. It tells us about the environment where it was born. By studying the strange chemistry of 3I Atlas, scientists could begin to piece together the secrets of an alien birth. They could start to imagine the kind of star system it came from, and how different it might have been from our own. The unusual dominance of carbon dioxide in 3I Atlas strongly suggests that it formed in a stellar nursery, very different from the one that gave birth to our Sun. A stellar nursery is a giant cloud of gas and dust where new stars are born. As a star forms, the leftover material flattens into a spinning disk around it. This is called a protoplanetary disk. It is within this disk that planets, asteroids and comets are made. The composition of this disk, what it's made of and what the temperatures are like at different distances from the new star, determines the kinds of objects that will form. The chemistry of 3I Atlas points to a birthplace that was either much colder than our early solar system's comet-forming region, or had a much higher concentration of carbon-based molecules. In our solar system, comets formed in an area where water ice was plentiful. In the home system of 3I Atlas, it seems that carbon dioxide ice was the most common frozen material available. This small difference has huge implications. It tells us that the raw ingredients for making planets can vary significantly from one star system to another. A comet's chemical signature is like a direct record of its birth story. It's a fossil, not of ancient life, but of ancient chemistry. The molecules frozen inside a comet have been preserved for billions of years, locked in a deep freeze as the comet travelled through the cold of space. When Webb's instruments analysed the gases coming off 3I Atlas, they were essentially reading a message from the distant past. This message hinted at different temperatures, different pressures, and different raw materials in its home system's planetary disk. For example, if the gas cloud that formed its parent star was richer in carbon and oxygen than our Sun's cloud was, it would naturally lead to the formation of more carbon dioxide. This would change everything about the way planets in that system might form. Perhaps it led to the creation of carbon planets, instead of rocky, water-rich planets like Earth. 3I Atlas is a physical piece of evidence, a sample from that alien environment that we can study directly. Scientists have a concept called the ice line, or frost line. This is the distance from a young star where it becomes cold enough for a particular substance to freeze into ice. In our solar system, there is a water ice line. Inside this line, closer to the Sun, it's too warm for water ice to exist, so we have rocky planets like Earth and Mars. Outside this line, it's cold enough for water to freeze, which is why the giant planets like Jupiter and Saturn have icy moons, and why comets are full of water ice. The chemistry of 3I Atlas suggests that it might have formed near a carbon dioxide ice line in its parent system. This would be a region where the temperature was just right for carbon dioxide to freeze, but perhaps too warm for other gases like nitrogen or methane to freeze as easily. If the environment in its planetary disk was structured around a carbon dioxide ice line instead of a water ice line, the whole process of planet formation would have been different. The building blocks available to make planets and comets would have been fundamentally different from the ones that built our solar system. This single discovery, that 3I Atlas is so rich in carbon dioxide, has a profound meaning. It tells us that planets and comets can form in many different ways across the galaxy. It shows that our solar system is not necessarily the standard model for how things work. The universe is not a factory that produces identical solar systems over and over. Instead, it's more like a giant laboratory where countless different experiments are running at once. Each star system can have its own unique set of starting conditions, its own unique blend of chemical building blocks. This diversity is exciting. It means there could be types of planets and comets out there that we haven't even dreamed of yet. 3I Atlas is our first concrete evidence of this diversity. It proves that the processes that build worlds are flexible and can work with different ingredients. It expands our understanding of what is possible in the cosmos. This also forces us to reconsider what we look for when we search for life elsewhere. We often focus on finding planets with liquid water, because life on Earth depends on it. But if other solar systems are built with different chemical foundations, perhaps life could arise in ways we don't yet understand. The story of 3I Atlas is a reminder to keep an open mind. The way our world was made is just one way. Its journey from a distant, unknown star system to our own brings a powerful message. The galaxy is a place of immense variety and endless possibility. We are just beginning to appreciate the full, complex tapestry of cosmic creation. By studying this single, tiny visitor, we are learning not just about its home, but about the fundamental rules that govern the birth of all stars and planets, including our own. The secrets of its alien birth are, in a way, secrets about the nature of the universe itself. The implications ripple outward. If comets are responsible for delivering water and organic molecules to young planets, as many scientists believe they did, for Earth, then the type of comet matters. A planetary system bombarded by water-rich comets would evolve very differently from one bombarded by carbon dioxide-rich comets, like 3I Atlas. The chemistry of the planet's atmosphere, its oceans, and its potential to host life would all be shaped by these early deliveries. 3I Atlas shows us that the delivery service of the cosmos might offer very different packages to different worlds. This messenger from afar is not just telling us about its own past, it is forcing us to imagine countless other pasts and countless other presents for worlds scattered throughout our galaxy. While the huge amount of carbon dioxide was the headline discovery, it was only the beginning of the story. The James Webb Space Telescope's powerful instruments could see more than just one molecule. They peered deep into the chemical soup surrounding 3I Atlas, identifying a whole list of ingredients. Each one added a new layer to the story of this cosmic wanderer. This was our chance to unpack the comet's DNA, to find out about all the other hidden ingredients it carried on its long journey. Besides the shocking amount of carbon dioxide, Webb also found many other familiar substances. It detected water vapour, confirming that 3I Atlas does contain some water ice, even if it's not the main component. This was an important discovery. It showed that while the comet's chemistry was exotic, it wasn't completely alien. It still contained the most essential molecule for life as we know it. Webb's instruments also found carbon monoxide, another common gas found in comets. It found evidence of water ice grains mixed in with the dust, and different kinds of dust itself, including silicates, which are the minerals that make up rocks on Earth. There were also tiny bits of other gases, like carbonyl sulfide, a sulfur-containing molecule. This detailed list of ingredients was like a recipe for the comet. By studying the proportions of each substance, scientists could learn even more about its home. Each of these molecules helped scientists understand the conditions where 3I Atlas formed and what happened to it during its long trip through space. For example, the ratio of carbon monoxide to carbon dioxide can tell us about the temperature of the region where it was born. The presence of sulfur-containing molecules like carbonyl sulfide might give clues about the role of volcanic activity or other energetic events in its home system. The type of dust grains reveals information about the rocky materials available to build planets. It's a bit like a detective analysing the mud on a suspect's shoes. The different types of soil, pollen and minerals in the mud can tell the detective exactly where the suspect has been. In the same way, the different molecules in 3I Atlas are clues that point back to its origin story, helping scientists to reconstruct the environment of a star system light years away. The fact that 3I Atlas still has so many different chemicals is remarkable. It means the comet managed to keep its original makeup, even after travelling for billions of years through the harsh environment of interstellar space. This journey is not a gentle one. The comet would have been exposed to cosmic rays, radiation, and perhaps even heat from passing near other stars. These things could have changed its chemistry, boiling away the more delicate ics, or altering the molecules on its surface. But Webb's observations show that the comet's interior was well preserved. It acted like a perfect time capsule protecting its ancient frozen secrets. This suggests that the outer layers of the comet might have formed a protective crust, shielding the pristine material inside. When the comet got close enough to our Sun, the heat was finally strong enough to break through this crust and release the gases that had been trapped for eons. We were lucky enough to be there to witness it. Webb's observations also gave us a clue about how these gases were escaping. The instruments could not only identify the gases, but also map where they were coming from. The results were interesting. The gases weren't just shooting out from one or two active spots on the comet's surface like geysers. Instead, they seemed to be coming out from all over the side of the comet that was facing the Sun. The entire sunlit hemisphere appeared to be active, steadily releasing its ancient frozen gases into space. This widespread activity gave scientists more clues about the comet's physical structure. It was not just a solid, dead rock with a few cracks. It was an active, dynamic world. This observation suggests two possibilities about the comet's internal structure. One idea is that the comet's nucleus, its solid core, might be very porous. This means it could be full of tiny holes and channels, like a sponge. When the Sun heats the surface, the heat can travel down into these channels, warming up ices buried deep inside. This would cause gas to be released from a wide area, not just a single vent. Another possibility is that the surface of the comet has many different active spots, or vents, that are too small and too close together for Webb to see individually. The combined effect of all these small jets of gas would look like the entire surface is active. Either way, it tells us that the inside of 3I Atlas is not a simple, solid block of ice and rock. It has a complex structure that allows it to release its gases in a very efficient way. This physical structure is just as important as its chemical makeup for understanding the comet's history and behavior. Unpacking the comet's DNA is a slow and careful process. Scientists around the world are still analysing the rich data from Webb, looking for even more hidden ingredients and clues. Each new molecule they can identify adds another word to the message this comet has carried across the galaxy. The water tells us its home had the building blocks for life, the carbon. Dioxide tells us its home was different from ours. The dust tells us about the rocks that might have formed planets there, and the other trace gases add more and more detail to the picture. Together, these ingredients are painting a portrait of a distant solar system, a place we can study and explore through this remarkable visitor. 3I Atlas has proven to be a treasure chest of chemical information, and we're just beginning to sort through the jewels inside. The deeper scientists looked into the data from 3I Atlas, the more puzzles they found. Beyond its strange chemistry, the comet's physical body presented its own set of mysteries. How big was it? How heavy was it? And why was it behaving in a way that seemed to defy the normal rules for comets? Answering these questions was crucial for building a complete picture of this interstellar traveller. But the more they learned, the more they realised how little they knew. The comet's strange body, its size, its mass and its behaviour, all pointed to a deeper cosmic mystery. One of the first and most basic questions scientists asked was, how big is 3I Atlas? Knowing the size of the comet's nucleus, its solid core is incredibly important, but measuring it is very difficult. The nucleus is tiny, and it's hidden inside the huge fuzzy cloud of gas and dust called the coma. It's like trying to measure the size of a single bee inside a massive swarm. Scientists have to use indirect methods to estimate its size. By looking at how much light it reflects and how much gas it's producing, they can make an educated guess. Current estimates suggest that the nucleus of 3I Atlas is somewhere between 1.4 and 5.6 kilometers across. That's a pretty wide range, showing how uncertain the measurement still is. For comparison, that's about the size of a small mountain or a small city. Getting a more precise measurement is a key goal for future observations. Knowing the comet's exact size is important for several reasons. First, it helps us understand how the gases escape from its surface. A larger object has more gravity, which can make it harder for gas to leave. A smaller object has less gravity, so gas can escape more easily. The size also affects how heat from the sun gets into the comet's interior. A larger body takes longer to warm up, so the activity we see might be coming from layers just below the surface. A smaller body might heat up more quickly and all the way through. Knowing the size is a critical piece of the puzzle for understanding how the comet works. It helps turn our observations of the gas and dust into a real, physical model of the object itself. Another big puzzle is the comet's mass and density. How heavy is it, and how tightly packed is its material? Just like with its size, these are very hard to measure directly. But based on its estimated size and the way it's behaving, scientists have made some startling calculations. Current estimates suggest that 3I Atlas could weigh over 33 billion metric tons. This would make it one of the heaviest and most massive comets ever studied. If this is true, it would mean the comet is also very dense. Most comets in our solar system are not very dense. They are often described as fluffy or porous, more like a packed snowball than a solid rock. If 3I Atlas is truly this massive and dense, it would be another major way in which it is different from the comets we know. A high density might mean it formed in a region of its home star system where material was being squeezed together more forcefully, or that it's made of heavier elements. This surprising mass is another clue that points to a very different origin story. But perhaps the most baffling mystery of all is how the comet moves. When a comet gets close to the sun, the ice on its surface turns into gas and shoots out in powerful jets. These jets act like tiny rocket engines. They push on the comet, causing it to move in ways that can't be explained by gravity alone. This effect is called non-gravitational acceleration. We see it in almost all active comets. It's a normal part of their behaviour, but 3I Atlas is different. Despite all the gas that Webb saw streaming off its surface, the comet shows almost no non-gravitational acceleration. It is moving along a path that is almost perfectly predicted by the pull of gravity from the Sun and the planets. The powerful jets of gas don't seem to be pushing it around at all. This is very, very unusual. For a comet to be so active, producing so much gas but not be pushed by that gas, is a major contradiction. It challenges our basic understanding of how comets work. Scientists have a few ideas that might explain this strange behaviour, but none of them are perfect. One idea is that the comet is simply incredibly massive and dense, as the other estimates suggest. If it's heavy enough, the push from the gas jets might be too weak to change its path in a noticeable way. It would be like trying to move a giant boulder by blowing on it. Another idea is that the comet's nucleus is very strong inside. Perhaps it has a tough, solid structure that doesn't allow the jets to form in a way that pushes the whole object. A third idea is that the comet has a special structure that cancels out the push. For example, if the jets of gas are coming out perfectly evenly from all sides, their forces might balance each other out, resulting in no net push. Or perhaps the comet is spinning in such a way that the push from the jets averages out over time. Each of these possibilities paints a picture of a very strange object. A supermassive, ultra-dense comet would be a new class of object. A comet with a very strong internal structure would challenge the idea that comets are fragile, fluffy balls of ice. A comet with perfectly balanced jets would imply a very unusual shape or rotation. Whatever the answer is, the strange motion of 3I Atlas is one of its biggest mysteries. It tells us that there is something fundamentally different about its physical body, not just its chemical makeup. Solving this puzzle will be key to understanding not only this visitor, but the entire population of interstellar objects that might be roaming our galaxy. It's a cosmic mystery that has scientists scratching their heads and eagerly awaiting more data that could finally shine a light on the truth. The journey of 3I Atlas is a story written across an almost unimaginable stretch of time. This object is not just a visitor from another place, it is a traveller from another era. As scientists studied its path and its properties, they came to a mind-bending conclusion. This small, dark object might be incredibly ancient, possibly older than our own Sun and all the planets that circle it. It is a true time traveller from deep space, a relic from a past so distant it challenges our imagination. Based on its trajectory and speed, scientists can make estimates about how long 3I Atlas has been travelling through interstellar space. The numbers are staggering. The estimates suggest the comet could be between 3 and 11 billion years old. Let's pause to think about that. Our solar system, including the Earth and the Sun, is about 4.6 billion years old. This means that 3I Atlas could have been born long before our own world even existed. It might have formed around one of the galaxy's earlier generations of stars. It could have been wandering the void while our own solar system was just a cloud of gas and dust waiting to be born. If this is true, then 3I Atlas is more than just a comet. It's like a fossil from the early days of our galaxy. It holds clues about what the Milky Way was like billions of years ago. The chemical makeup of the galaxy changes over time. Early stars create heavier elements, which are then scattered into space when the stars die. These heavier elements become part of the next generation of stars and planets. By studying the composition of an ancient object like 3I Atlas, we can get a direct sample of the chemical environment of the galaxy from a long-gone era. It's like an archaeologist finding a perfectly preserved tool from a lost civilization. This comet is a tool that can help us dig into the deep history of our own galaxy, telling us about the primordial materials that were available to build the first planets. Another clue to its incredible age and long journey is its extreme speed. At 210,000 kilometers per hour, it's moving even faster than the previous interstellar visitors, Oumuamua and 2I Borisov. This incredible velocity is hard to achieve. It hints at a much older origin and a much longer, more eventful journey through the galaxy. Over billions of years, an object travelling through the Milky Way can have its speed changed by passing near other stars or giant clouds of gas. Each close pass can act like a gravitational slingshot, either speeding the object up or slowing it down. The very high speed of 3I Atlas suggests it may have had many such encounters over a very long time, each one adding a little more energy to its motion. It's like a pinball that has been bouncing around the galaxy for eons, getting faster and faster with each bounce. This speed is a testament to the epic length of its voyage. This tremendous speed also tells us something about how it began its journey. An object doesn't get thrown out of its home star system with such force for no reason. Its ejection must have been caused by a very powerful and violent event. One possibility is a close encounter with another star. If another star passed very close to its home system, the gravitational pull could have disrupted the orbits of the comets and planets, flinging some of them out into deep space at high speed. Another, more likely possibility is that it was thrown out by the giant planets in its own system. In the early days of a solar system, giant planets often move around, their orbits shifting and changing. This process is called planetary migration. As these giant worlds move, their immense gravity can act like a catapult, launching smaller objects like comets completely out of the system. The high speed of 3I Atlas suggests that the event that ejected it was particularly powerful. It was not a gentle nudge out the door, it was a violent kick into the interstellar void. These events show us that interstellar comets are not just gentle wanderers, they are survivors. They are the leftovers of massive cosmic disruptions. The formation of a planetary system can be a messy and chaotic process. For every planet that forms and settles into a stable orbit, many other smaller objects can be lost, thrown away into the galaxy. The existence of objects like 3I Atlas is direct evidence of this chaos. They are the witnesses to the wild and violent youth of other solar systems. By studying them, we learn about the powerful gravitational forces that shape planetary systems across the galaxy. We learn that for every quiet, orderly solar system like our own appears to be today, there was likely a tumultuous past filled with planetary migrations and cosmic collisions. So when we look at 3I Atlas, we are seeing more than just a comet. We are seeing a survivor of cosmic violence and a messenger from the deep past. It has travelled farther and longer than we can truly comprehend. It was born in a different time, in a different place, under different conditions. It has witnessed billions of years of galactic history, silently soaring through the dark. Its journey through our solar system is a brief, fleeting moment in its ancient life, but for us, that moment is a golden opportunity. It's a chance to touch a piece of history, a relic from a time before the Earth was formed. This ancient traveller carries the secrets of its birth, its violent ejection, and its long, lonely voyage. It is up to us, with our telescopes and our curiosity, to read the story it has carried for so long. The journey of 3I Atlas through the vast, empty space between the stars was not a peaceful one. For billions of years it had to endure a gauntlet of cosmic dangers. The fact that it arrived in our solar system still intact, still rich with its original frozen gases, is a testament to its incredible resilience. It is a true survivor of the void. Understanding the challenges it faced helps us appreciate just how special and tough this object really is. During its billions of years in interstellar space, 3I Atlas had to survive many dangers that would destroy weaker objects. The space between stars is not completely empty. It is filled with radiation, fast-moving particles, and tiny grains of dust. Over eons, these things can take a toll. One of the biggest dangers is cosmic rays. These are tiny, powerful particles, mostly protons, that are shot out by exploding stars and other high-energy events across the galaxy. They travel at nearly the speed of light and can penetrate deep into solid objects. Over billions of years, 3I Atlas would have been constantly bombarded by these cosmic rays. This relentless shower of particles could have changed the chemical makeup of its surface, breaking down complex molecules and forming new ones. Scientists believe this processing by cosmic rays could create a tough, dark, organic-rich crust on the comet's surface. This crust might have acted as a shield, protecting the pristine ices buried deep inside. Another constant threat was the rain of tiny space dust or micrometeorites. While interstellar space is mostly empty, it does contain very small particles of dust. As 3I Atlas sped through the galaxy, it would have been constantly running into these particles. Each impact, though tiny, would have been like a microscopic explosion on its surface, chipping away a few molecules. Over billions of years, this steady erosion could have worn away meters of the comet's outer layers. It's like a rock in a river being slowly smoothed down by the constant flow of water and sand. For 3I Atlas to have survived this process and still be several kilometers in diameter, it must have been a much larger object when it first began its journey. It has been slowly whittled down by its long and dusty travels. The comet also would have faced threats from other stars. While space is vast, its journey might have taken it relatively close to other star systems. When passing near another star, even at a great distance, The star's heat would have warmed the comet's surface. This would have caused some of its most volatile ices, like frozen nitrogen or carbon monoxide, to turn into gas and escape. Then, as it moved away, it would have cooled down again. This process of heating and cooling is called thermal cycling. It can put a lot of stress on the internal structure of a comet. Imagine taking a frozen rock and repeatedly warming it up and cooling it down. Cracks would start to form. The rock could eventually break apart. 3I Atlas must have a very strong internal structure to have survived potentially thousands of these thermal cycling events over its lifetime without shattering into pieces. The fact that 3I Atlas is still active today, with enough gas and ice to create a large coma, is perhaps the most impressive evidence of its toughness. After billions of years of cosmic ray bombardment, micrometeorite erosion, and thermal stress, it still has a vast reservoir of its original, pristine material locked away inside. This suggests that the protective crust formed by cosmic rays was very effective. It acted like a spacesuit for the comet, shielding its fragile interior from the harsh environment of interstellar space. It was only when it got close to our Sun, with its intense heat, that this ancient crust was finally breached, allowing the primordial gases to escape for the first time in eons. We are witnessing the uncorking of a bottle that has been sealed for billions of years. Its journey might have also taken it through different kinds of interstellar environments. The space between stars is not uniform. There are vast empty bubbles of hot gas, and there are dense cold regions called molecular clouds. These clouds are the stellar nurseries where new stars and planets are born. If 3I Atlas passed through one of these clouds, it would have been a very different experience. The dense gas and dust in the cloud could have added new material to the comet's surface, coating it with a fresh layer of interstellar matter. The chemicals in the cloud could have reacted with the comet's surface, changing its composition. So, the comet we see today is not just a product of its birthplace. It is also a product of its long and varied journey. Its surface layers may contain a record of all the different cosmic environments it has travelled through. It's a true galactic historian, carrying the dust of 1,000 light-years on its back. Surviving the void for billions of years is an extraordinary feat. It requires a combination of size, strength, and perhaps a bit of luck. 3I Atlas has proven that it has what it takes. It is a rugged, ancient survivor that has weathered the worst the galaxy can throw at it. Its arrival in our solar system is the final chapter of an epic journey of survival. By studying its scars, its protective crust, and its pristine interior, we can learn about the dangers that lurk in the space between the stars and about the incredible endurance of these cosmic travellers. It is a story of resilience written across the vastness of space and time. The arrival of a rare visitor like 3I Atlas was too big a moment for any single observatory to handle alone. To unlock the secrets of this interstellar comet, a global effort was needed. Scientists from all over the world knew that this was a fleeting opportunity, and they had to work together to gather as much information as possible. This cooperative spirit led to one of the most impressive scientific collaborations in recent memory. The mission to study 3E, Atlas became a shining example of how a united world can achieve incredible things. It was a case for the Galactic detective team. Studying 3I Atlas involved one of the biggest multi-observatory campaigns ever organised for an interstellar visitor. A campaign like this is a coordinated effort where many different telescopes, both on the ground and in space, all observe the same object at the same time or in a planned sequence. The goal is to collect as much data as possible across the entire spectrum of light, from radio waves to X-rays. As soon as 3I Atlas was confirmed to be interstellar, messages flew across the internet. Astronomers alerted their colleagues at observatories around the globe. Telescope schedules were changed. New observation plans were rapidly drawn up. It was an all-hands-on-deck moment for the astronomy community. The world's most powerful eyes were all turning to look at this single, faint speck of light as it raced through our solar system. The reason for this teamwork is simple. No single telescope could have gathered all the necessary information. Each observatory has its own unique strengths. Some telescopes are designed to take incredibly sharp pictures in visible light. Others are built to detect the faint heat of infrared light. Still others can analyze ultraviolet light or even radio waves. By combining the data from all these different instruments, scientists can build a much more complete picture of the comet. It's like a group of detectives investigating a crime scene. One detective might be an expert at finding fingerprints, another might specialize in analyzing fibers, a third might be good at interviewing witnesses. By working together and sharing what they find, they can solve the case much faster and more effectively than any one of them could alone. In the same way, each telescope provided a unique clue about 3I Atlas. The James Webb Space Telescope gave us the chemical fingerprints in infrared. The Hubble Space Telescope provided sharp images in visible light, and telescopes on the ground monitored its behavior day after day. This global collaboration was crucial. The comet was only going to be here for a short time, and its appearance would change as it got closer to the Sun. It was important to have continuous coverage, to watch how it evolved. Telescopes in different parts of the world could work together to keep an eye on it around the clock. When it was nighttime in Hawaii, and the telescopes on Mauna Kea could see it, it was daytime in Chile. But the telescopes in the Andes Mountains could pick up the watch as the Earth turned. Space telescopes like Webb and Hubble added another layer, able to observe without being affected by weather or the day-night cycle. This network of observatories created a constant, unbroken stream of data, ensuring that no important changes in the comet's behavior were missed. Each observatory added its own unique abilities to the investigation. For example, large, ground-based telescopes can use giant mirrors to collect a lot of light, allowing them to study very faint details of the comet's coma and tail. They can also use instruments called polarimeters, which study how light is scattered by the dust particles. This gives clues about the size, shape, and texture of the dust. Space telescopes, on the other hand, can see wavelengths of light that are blocked by Earth's atmosphere, like certain types of infrared and ultraviolet light. These wavelengths are often where the most important chemical signatures are found. By looking at the comet in all these different kinds of light, scientists could piece together a full picture. The visible light showed them the dust. The infrared light showed them the gas. The ultraviolet light showed them the effects of the sun's radiation. Together, these different views created a multi-dimensional understanding of this complex and mysterious object. The spirit of collaboration extended beyond just collecting the data. Scientists from dozens of countries shared their findings openly, publishing their results quickly so that other researchers could build on them. They held online meetings to discuss their interpretations and debate new ideas. This open and cooperative environment accelerated the pace of discovery. An idea sparked by data from a telescope in Chile could be tested the next day with observations from a telescope in space. This global teamwork is a hallmark of modern astronomy. The universe is too big, and its mysteries are too deep for any one person or any one country to solve alone. The story of 3I Atlas is not just a story about a comet, it's also a story about human curiosity and our ability to work together to reach for the stars. The Galactic detective team was a global one, united by a shared passion for understanding our place in the cosmos. This massive effort highlights a fundamental truth about exploring the unknown. To solve the biggest puzzles, we need many different perspectives. Every telescope, every instrument, and every scientist brings a unique piece to the puzzle. The campaign to observe 3I Atlas was a beautiful demonstration of this principle in action. It was science at its best, collaborative, global, and relentless in its pursuit of knowledge. The secrets of this interstellar visitor were being unlocked not by a single hero, but by a worldwide team of dedicated detectives, all working together to read the message it had carried from so far away. While the James Webb Space Telescope provided the groundbreaking chemical analysis, it was part of a larger team. To build a complete profile of 3I Atlas, we needed different perspectives. The Hubble Space Telescope, Webb's older sibling in space, provided a crucial view in a different kind of light. And down on Earth, a network of powerful ground-based telescopes acted as our planet's eyes, watching the comet's every move. Each of these observatories added a vital piece to the puzzle, helping to create a richer and more detailed understanding of our interstellar guest. The Hubble Space Telescope played a very important role in the campaign. On July 21st, 2025, when 3I Atlas was still about 277 million miles from Earth, Hubble turned its famous eye toward the visitor. Hubble sees the universe primarily in visible and ultraviolet light, the same kinds of light our eyes can see, plus a little more. This is a perfect complement to Webb's infrared vision. While Webb is a master at seeing the invisible heat signals from gas molecules, Hubble excels at taking incredibly sharp pictures of the dust that surrounds a comet. Dust particles reflect sunlight, making them glow brightly in visible light. Hubble's images of 3I Atlas were stunningly clear. These images showed a distinct teardrop shape in the dust cloud or coma around the comet's nucleus. This shape was a crucial clue. It helped scientists understand how the dust was spreading out into space and how fast the comet was losing mass. The teardrop shape is caused by the pressure of sunlight. As the comet releases dust, the sunlight physically pushes on the tiny dust particles, sweeping them back and away from the sun. This creates the classic comet tail. By analysing the precise shape and brightness of this dust cloud, scientists could calculate things like the size of the dust particles and the rate at which the comet was shedding them. This information from Hubble provided a vital context for Webb's findings. Webb told us what the gas was made of, and Hubble showed us how the dusty leftovers were behaving. This visible light view from Hubble was essential for understanding the big picture. It helped explain how the dust interacts with sunlight, and how the entire gas and dust cloud, the coma, changes over time. For example, by comparing Hubble images taken at different times, scientists could watch for sudden outbursts of activity, where the comet might unexpectedly release a large amount of dust and gas. These outbursts can reveal clues about the comet's internal structure and rotation. The combination of Webb's chemical data and Hubble's structural data was powerful. It was like having two different senses to study the comet. Webb was like our sense of smell, telling us what the comet was made of. Hubble was like our sense of sight, showing us what it looked like and how it was put together. Together, they gave us a much more complete experience of this alien object. Meanwhile, back on Earth, an army of telescopes was also on the case. Powerful observatories like the Gemini South Telescope in Chile and the Gemini North Telescope in Hawaii were constantly watching 3I Atlas. These ground-based telescopes have a key advantage: flexibility. They can be pointed at a target much more quickly than a space telescope, and they can watch it for hours at a time. This allowed them to provide a continuous look at the comet's behaviour. They watched how the comet's tail grew and changed from night to night. They measured how its brightness changed as it moved closer to the sun. This continuous monitoring is crucial for catching rapid changes that a space telescope, which has a very busy schedule and can only look at an object for a limited time, might miss. These ground-based observations provided the essential timeline for the story of 3I Atlas. They tracked its journey, creating a day-by-day log of its activity. This long-term data is the backbone of the entire research campaign. It provides the context for the detailed snapshots taken by Webb and Hubble. For example, if Webb detected a certain mix of gases on one particular day, the ground-based data could tell us if the comet was in a quiet phase or in the middle of an outburst at that exact moment. This helps scientists to correctly interpret the more detailed but less frequent data from space. The partnership between ground and space telescopes is one of the most powerful tools in modern astronomy. In a clever piece of detective work, scientists even looked back in time. They searched through old sky survey data from before 3I Atlas was officially discovered. They were looking for faint images of the comet that might have been accidentally captured weeks or even months earlier, and they found them. These pre-discovery images were incredibly valuable. They allowed scientists to track the comet's path and behaviour over a much longer period of time. This helped them to refine their calculations of its orbit, confirming with even greater certainty that it was indeed from interstellar space. It also gave them a baseline of its activity when it was farther away from the Sun. By comparing this early behaviour to its later, more active phase, they could learn how the comet woke up as it approached the warmth of our star. This archival research was a brilliant way to extend our window of observation, giving us a longer look at this incredible, once-in-a-lifetime visitor. As the picture of 3I Atlas became clearer, scientists started using even more advanced and subtle techniques to study it. They were not just looking at the brightness or the colour of its light anymore. They were analysing its properties in ways that revealed hidden secrets about the very nature of its dust and the presence of water that was hard to see directly. These investigations, using tricky concepts like twisted light and specialised space observatories, added even more layers to the comet's growing mystery. One of the most advanced techniques used to study 3I Atlas is called polarimetry. This sounds complicated, but the basic idea is simple. Light normally vibrates in all directions. When sunlight bounces off a surface, like the dust grains in a comet's coma, it can become polarized. This means it starts vibrating more in one direction than in others. It's the same principle used in polarized sunglasses, which block out the polarized glare of light reflecting off a road or water. By measuring the amount and direction of polarization in the light from 3I Atlas, scientists can learn a lot about the dust particles that reflected it. The results from these studies were fascinating. They showed that the dust from 3I Atlas had some of the most unusual optical properties ever seen in a comet. The dust grains in its coma were scattering sunlight in a very unique way. This suggested several possibilities. The dust particles might be unusually small, even smaller than the dust from comets in our solar system. Or they might have very strange surfaces, perhaps with a complex porous texture that traps and re-emits light in a peculiar way. The way the polarization changed as the viewing angle changed also gave clues. It hinted that the dust might be made of a different material, or have a different structure than the fluffy dust aggregates we see in our own comets. These unique light-scattering properties were another major clue that 3I Atlas was a fundamentally different type of object. It wasn't just its gas that was strange, its dust was strange too. This finding expanded our understanding of the kinds of solid materials that can exist in other star systems. It suggested we might be looking at a completely new class of cosmic dust. While Webb had found that carbon dioxide was the dominant gas, scientists were still eager to confirm the presence of water and measure it more accurately. Water is a notoriously difficult molecule to detect from Earth, as our own atmosphere is full of it. To get a clear view, you need a space telescope that can see in the ultraviolet part of the spectrum. For this job, scientists turned to the Neil Gehrels Swift Observatory. Swift is a satellite whose main job is to hunt for gamma-ray bursts, the most powerful explosions in the universe. But it also has a powerful ultraviolet telescope. In ultraviolet light, the breakdown products of water become visible. When sunlight hits a water molecule, H2O, it can break it apart into a hydrogen atom, H, and a hydroxyl radical, OH. This hydroxyl radical gives off a clear signal in ultraviolet light. By looking for this signal, Swift could find hidden water, and it found it. Swift's special ultraviolet observations detected the clear signature of hydroxyl radicals in the coma of 3I Atlas. This was the smoking gun that proved water was indeed escaping from the comet. By measuring the strength of this signal, scientists could calculate how much water was being released. The observation suggested that about 40 kilograms of water per second were escaping from the comet, when it was about 3.5 times farther from the Sun than the Earth is. That sounds like a lot, but it was still far less than the amount of carbon dioxide being released. This confirmed what Webb had seen. Carbon dioxide was the king on this comet. But it also proved, without a doubt, that a significant amount of water ice was also present inside the nucleus. This confirmation was important. It showed that even in a carbon dioxide-dominated world, water was still a key ingredient. The observation also gave clues about how much of the comet's surface was active. Based on the amount of water being released, scientists estimated that about 20% of the comet's surface might already be active, even at that great distance from the Sun. This was a high number, suggesting again that the comet was not a dormant rock, but a very dynamic and active body. The combination of the polarimetry data and the ultraviolet observations painted a more complete and more complex picture. We now knew its dust was strange and that it definitely had water, but in unusual proportions. Each new discovery seemed to add another layer of strangeness to this visitor. 3I Atlas was refusing to fit into any of our neat little boxes. It was forcing us to create new ones. These advanced observations showcase how modern astronomy works. It's not just about taking a pretty picture. It's about using every trick in the book, every sophisticated tool at our disposal, to squeeze every last drop of information from the faint light of a distant object. By studying the twist of light and searching for the faint ultraviolet glow of broken water molecules, scientists were able to uncover secrets that would have otherwise remained completely hidden. The mystery of 3I Atlas was deepening, and its story was becoming richer with every new clue. Just when scientists thought 3I Atlas could not get any stranger, another surprising discovery emerged from the data. Buried within the complex chemical signatures of the comet's coma, some observations reported finding traces of a metal, nickel. This was an intriguing and unusual finding. While metals are a component of the rocky dust in comets, they are not usually a major focus of study because they are hard to detect in the gas phase. The presence of nickel, a metal known for its ability to withstand high temperatures, added another fascinating clue to the puzzle, hinting at a potentially high-energy origin for this ancient wanderer. The detection of nickel in the coma of 3I Atlas was a subtle but important finding. When comets get very close to the Sun, the heat can become intense enough to vaporize not just ices, but also some of the rocky materials and metals mixed in with them. Finding nickel in the gas surrounding 3I Atlas means that some of the dust it was releasing contained metals, and that conditions were right for these metals to turn into gas. This tells us that the solid material in 3I Atlas is not just simple rock and ice, it contains more complex heat-resistant components. This is another piece of evidence that the building blocks of its home star system were different from our own. The presence of nickel could mean that 3I Atlas formed in, or was changed by, very energetic environments. One possibility is that it formed in a region of its parent star's disk that was very hot, perhaps closer to its star than where our own comets formed. In such a region, more metals would have been present in the material that clumped together to form the comet. Another, more dramatic possibility is that the material in the comet was exposed to some kind of shock heating event in its past. A shock wave, perhaps from a nearby exploding star or from turbulence within the protoplanetary disk, could have rapidly heated the dust grains, baking the metals into them. This would create a very specific kind of metallic dust, different from the kind that forms in quieter conditions. This metallic finding, when combined with the other strange properties of 3I Atlas, creates a truly unique chemical profile. We have an object that is overwhelmingly dominated by carbon dioxide, a substance that freezes at very cold temperatures, yet it also seems to contain traces of nickel, a metal that is associated with high temperatures. This combination of cold and hot chemical signatures is puzzling. It's like finding a polar bear and a desert lizard living in the same cage. It suggests that the comet's history might be very complex. Perhaps it formed in a cold region but was later exposed to a blast of heat. Or maybe the protoplanetary disk it came from was very turbulent, with hot metal-rich material from the inner regions getting mixed with cold, icy material from the outer regions. This discovery forces us to think about planetary formation in a more dynamic way. We often imagine it as a calm and orderly process, with different materials neatly sorted by temperature at different distances from the star. But the chemical profile of 3I Atlas suggests it can be a much messier process. It hints at a chaotic environment where materials from different regions are violently mixed together. This mixing could be driven by the gravity of giant planets moving through the disk, or by explosive events from the young star itself. This picture of a chaotic and mixed-up birthplace is actually consistent with some of the newest and most advanced models of how planetary systems form. 3I Atlas might be the first direct physical evidence we have that these chaotic mixing processes are real and important in other star systems. The nickel clue, though small, opens up a whole new line of questioning for scientists. They will now be looking more carefully for other metals and heat-resistant minerals in the data from 3I Atlas. Finding them could help confirm the idea of a high-energy origin. It also means that future studies of interstellar comets will pay much closer attention to the metallic content of their dust. This single, small discovery could lead to a whole new area of comet science. It's another example of how this one visitor is changing the way we look at the universe. It is teaching us to look for clues in unexpected places and to be prepared for surprising combinations of ingredients. The story of 3I Atlas is a story of contradictions, cold and hot, familiar and alien. And it is in these contradictions that the most exciting secrets are often found. As 3I Atlas continues its silent journey through our solar system, the story is far from over. In fact, the most dramatic chapter is yet to come. The comet is on a path that will take it closer and closer to our Sun, where the heat and radiation will become incredibly intense. Scientists are watching with anticipation, wondering what will happen next. How will the comet change as it faces the full power of our star? This next phase of its journey is critical, but observing it will present its own unique set of challenges. As 3I Atlas moves closer to the Sun, with its closest approach expected in late October 2025, scientists expect to see huge changes in its activity. The Sun's energy increases dramatically with proximity. As the comet heats up, ices that were stable in the colder outer solar system will begin to turn into gas. We might see new, different gases start to escape from the nucleus. For example, ices like methane or ammonia, which require more heat to sublimate than carbon dioxide, might start to boil off. This could reveal even more about the comet's deep interior composition. It's like peeling an onion. As each outer layer is stripped away by the sun's heat, we get to see a deeper, more pristine layer underneath. Scientists will be watching closely for these new chemical signatures to appear. The physical appearance of the comet is also expected to change dramatically. The coma will likely grow much larger and brighter. The tail could stretch for millions of kilometers across space. There is also a chance that the increasing stress from the heat and rapid gas release could cause the comet's nucleus to break apart. This is not uncommon for comets making their first pass close to the Sun. If it does fracture, it would be a spectacular event, giving us a rare glimpse of the fresh, unweathered material inside its core. Scientists are on high alert, ready to document any such changes, as they would provide an unprecedented look at the comet's internal structure. But observing this crucial phase of the journey comes with a major challenge. The most important part of its trip, when it is closest to the Sun and at its most active, will happen when the comet passes behind the Sun from Earth's point of view. This alignment is called solar conjunction. During this period, which could last for several weeks, the comet will be lost in the bright glare of the Sun. It will be impossible for telescopes on or near the Earth, including Hubble and Webb, to see it. It's a frustrating twist of cosmic timing. Just when the show is about to get really good, the curtains will close. This period of solar conjunction means that our most powerful eyes will be temporarily blind to the comet's behavior during its hottest, most active phase. This is a significant problem for scientists who want to understand the peak of its activity. They will have to wait patiently until the comet emerges from behind the Sun on the other side. When it reappears, it might look very different. Did it survive its close encounter? Did it break apart? Has its chemical output changed? Scientists will be eagerly waiting to see what state it is in after its trial by fire. During the blackout period, however, all is not lost. Scientists will have to get creative. They can rely on spacecraft that are orbiting the Sun, like the Solar Orbiter or the Parker Solar Probe. These spacecraft have different viewing angles and might be able to catch a glimpse of the comet even when it's hidden from Earth. Their data would be incredibly valuable, providing our only direct view of the comet during this critical time. Scientists can also use radio telescopes to try and detect signals from the comet. As radio waves are not as easily blocked by the Sun's glare, they will use every tool at their disposal to try and keep a faint connection to the comet during its passage behind the Sun. This is why the current detailed observations from the James Webb Space Telescope are so incredibly important. The data Webb is collecting now, while the comet is still visible, will be the benchmark. It provides a perfect before picture. Scientists are documenting its chemical makeup, its gas production rates, and its physical properties in exquisite detail. This data will be the standard against which any changes seen after it passes the Sun will be compared. By comparing the before and after states, they can figure out exactly how the intense heating from the Sun affected the comet. These precious observations are like a final, detailed health checkup before the patient undergoes a major ordeal. They are our last, best look at the pristine state of 3I Atlas before it faces its greatest test. The journey towards the Sun is a race against time for astronomers, a quest to gather as much data as possible before this cosmic visitor disappears into the light. The story of 3I Atlas is more than just the story of a single space rock. Its discovery and the incredible details we are learning about it have profound implications. This is not just another comet, it is a messenger from an unknown world, carrying a story that is changing our understanding of comets, star systems, and the history of our entire galaxy. The arrival of 3I Atlas matters because it is helping us to write a new cosmic story, one that is far richer and more complex than we ever knew. 3I Atlas is not just another comet, it's a cosmic ambassador from a different star. For the first time, we have a direct sample of the material that exists in another planetary system. Before the discovery of interstellar objects, everything we knew about other stars and their planets came from looking at their light from incredibly far away. It was like trying to understand a foreign country by looking at it through a blurry telescope from across an ocean. Now, with 3I Atlas, it's as if a piece of that foreign land has washed up on our shore. We can pick it up, study it, and analyze its composition directly. This gives us a unique and powerful look at how other solar systems might be built from the ground up. Its extreme chemical makeup and ancient age are forcing scientists to rethink long-held ideas about how comets form and change over time. For decades, Our theories were based entirely on the comets from our own solar system. We assumed they were the standard model for comets everywhere. 3I Atlas has shattered that assumption. Its carbon dioxide-rich composition shows us that there is more than one way to build a comet. This discovery forces us to broaden our theories and imagine a much wider range of possibilities for how planets and comets form around other stars. It is a powerful reminder that the universe is not required to follow the rules we've learned from our own small neighbourhood. There is a whole galaxy of diversity out there waiting to be discovered. The massive multi-telescope effort to study 3I Atlas highlights how modern astronomy has evolved. It is a testament to the power of global collaboration. The study of rare and fast-moving objects like this would be impossible for any single observatory. It requires a coordinated network of telescopes in space and on the ground, each contributing its unique strengths. The story of 3I Atlas is also a human story, a story of how scientists from around the world can set aside their differences and work together towards a common goal, the pursuit of knowledge. It showcases science as a unifying force for humanity. Studying 3I Atlas also helps us understand the vast, empty spaces between the stars and the objects that wander through them. We are learning about the incredible diversity of objects that are floating through our galaxy. Some, like Oumuamua, are deeply strange. Others, like 2I Borisov and 3I Atlas, are more recognizably comets, but with their own alien twists. By studying these visitors, we can start to build a census of the interstellar population. How common are they? What are they made of? And what do they tell us about the star systems they were thrown out of? It's a new field of astronomy, and 3I Atlas is one of its most important subjects. It's also teaching us about the harsh conditions these objects must survive on their billion-year journeys, giving us a new appreciation for their incredible resilience. This discovery opens a new window into the early universe. Because 3I Atlas may be billions of years older than our own Sun, it carries a chemical record of what the galaxy was like long ago. It is a sample of the primordial materials that form the stars and planets of a previous cosmic generation. By studying its composition, we can learn about the chemical evolution of our galaxy. We can see what raw ingredients were available in the past. It's a form of cosmic archaeology, allowing us to dig into the history of the Milky Way and understand the processes that eventually led to the formation of our own solar system, and ultimately ourselves. Ultimately, 3I Atlas is helping us piece together a bigger, more complex story of our place in the universe. It shows us that our solar system is not an island, but is connected to the wider galaxy through these wandering visitors. It shows us that the processes that formed our world are just one version of a story that is played out in countless ways around countless other stars. Each interstellar object is a new chapter in that grand galactic story. 3I Atlas, with its strange chemistry, its ancient age, and its mysterious body, has given us one of the most exciting and revolutionary chapters yet. It has challenged our assumptions, sparked new questions, and reminded us that there is always more to learn. The universe is constantly sending us messages in bottles. We just have to be ready to read them. What cosmic wonders will Webb find next? Stay curious, click that like button, and subscribe for more mind-blowing space discoveries.